Okay, so today we are going to discuss about the conversion of a regular expression to an NFA. Recall that we said that any language that can be accepted by a regular expression can also be accepted by an NFA and can also be accepted by a DFA. So today we are going to see an algorithm which is given a regular expression, it's going to construct an NFA for it. And we already know how to convert an NFA to a DFA, and we also know how to implement them. Alright, so here are the 5 different constructors for the regular expressions as we have studied. This is the single character C, where we assume that C belongs to sigma, the alphabet, epsilon, which represents the empty string. And then assuming that A is a regular expression and B is a regular expression, then A plus B is also a regular expression. Similarly, AB, which is a concatenation, is a regular expression, and then A star is a regular expression. A plus B represents union, if you recall. All right. So we're going to develop an algorithm that's going to construct given a regular expression, an arbitrary regular expression, something like, let's say, C plus D plus epsilon, star, and so on, right? So I could construct any arbitrary regular expression, and then we want to know, given a regular expression, we want to construct a corresponding NFA. So we are going to construct the NFA. To construct the NFA, we are going to do the same recursive method. So we're going to say, let's first construct an NFA for the whole expression. Let's first construct an NFA for the smaller expression on the left. Similarly, let's construct a regular expression for the smaller expression on the right. And then keep doing that, and so until we reach the base case, and then once we have the NFA for the base case, then we can from that construct the NFAs for the larger and larger expressions, right? So we're going to do this inductive construction of the NFA. To do this, we are going to assume that we're going to have some shape of an NFA. Well, it's a very simple shape. You have one start state. We assume that the NFA has only, let's say, one start state. If it has more than one start state, we can always add one unique start state and have epsilon moves from this unique start state from the unique start state to all the original start states. Similarly, we assume that we have a unique accepting state. Right? Once again, if there were more than one accepting states, we can always convert it to an NFA which has a unique accepting state through epsilon transitions. Alright, so with that, let's look at the base cases. So what would be an NFA that accepts the single character C? Well, it's easy. Let's do this with a blue pen. So this is my start state, and on receiving the single character C, it's going to end up in an accepting state. And so this is the NFA that accepts C and does not accept any other string. Similarly, what is an NFA that accepts the empty string epsilon? Well, this is also easy. Let's say this is a start state. Then I just make an epsilon transition and I reach my accepting state. All right. And this particular NFA accepts the empty string and does not accept any other string. Alright, now let's look at the higher level operators, the inductive operators. So A plus B, which is the union operator. So let's assume that for A we have already constructed an NFA which looks like the diagram shown on the slide. Similarly, for B we have constructed an NFA. We are now interested in constructing an NFA for A plus B. So how do we do that? Recall that A plus B indicates the union operator, which means that a string is accepted if it is accepted by either A or B. So if you want to represent the same fact in an NFA, what are we going to do? Well, we are going to just put the NFAs in parallel and say that if it accepts any of them, if the string is accepted by any of them, then it's accepted by the larger NFA. So to do this, we are going to have a start state. And then we're going to put these two NFAs, A and B. So this is the A NFA and this is the B NFA. Notice that in in this drawing, I'm not putting a concentric circle on the final state of A, because the final state of the whole NFA is going to be different from the final state, the accepting state of A or B, right? But these circles within the A automaton NFA is exactly the same, is exactly the accepting state of A. All right, and then we have a final state, our own final state. Okay, so now if we want to have an NFA that accepts strings from both, that would have been accepted by either A or B, well, we just connect this to A, the start state of A, and similarly the start state of B through epsilon transitions. So we can non-deterministically go into either of the NFAs, and if either of those NFAs accepts, then we are also going to accept. And to represent that, I'm just going to draw epsilon edges from their accepting states to the larger final accepting state. Okay, and so this particular NFA represents the NFA for A plus B given individual NFAs of A and B. Similarly, let's look at the concatenation operator. So once again, let's assume that we already have the NFAs for A and B, and we are interested in finding the NFA for AB. So once again, this is not very difficult. We're going to construct a start state, and then we are going to put A after this, and then we're going to connect the accepting state of A to the start state of B, which means that the string is accepted if one part of it is accepted, but the first part of it is accepted by A, and then with an epsilon transition, but by the way, these are epsilon transitions. So with an epsilon transition, we enter the automaton B, and then the rest of the string is accepted by B, and then we make an epsilon transition to our own final state. And this would be the NFA for the regular expression AB, given the NFAs for individual regular expressions A and B. Now finally, let's look at the iteration constructor, the last remaining constructor of the regular expressions. So let's say we have, once again, we have the NFA for A, and we are interested in constructing an NFA for A star. So once again, we'll have a start state, and we'll have an accepting state. And then what do we need to do? We want to say that what does A star accept? Well, one of the things that A star accepts is the empty string, so we're going to come to that. But it also accepts A or any number of repetitions of A. Right? So let's say this is A, and this is the final state of A. So what I'm going to do is I'm going to say that once I reach the final state of A, I can go back. These are all epsilon edges. I can go back to the non-deterministically go back to the start state, or I could non-deterministically decide to go to the accepting state. All right. So what does this automaton accept? It accepts one or more occurrences of A concatenated with each other. Okay, because I can non-deterministically choose to do 1A, 2As, 3As, and 4As before I move, and so on before I move to the final accepting state. There's one thing missing here. We also want to allow 0 occurrences of A, and in which case, to model that, we just add one more epsilon edge from our start state to the final accepting state. And so this is the iteration constructor.